record. Okay, so we're recording. So can you summarize?
Okay, so what we started to do is we went into the problem set, and Alfredo, what you did is you basically took each step of the equations and you represented them and multiplied them in MATLAB and got to the final result of equation TW, which is equation 3 for that paper, and you got the same matrices. What I did is I did it also, just to close the loop, I did it in a slightly different way. I took table 2, which is on page 7, the DH table basically, and I went through the normal DH procedure or DH transformation matrices, which is rotational Z times translate, just the normal function of the DH table, and I got the same end result. So this way we have derived each step and the final equation using just going through repeating the steps and doing the DH method as well.
Right. So the paper uses the rotation among the z-axis times the rotation about the y-axis multiplied by the displacement vector p, which is the one that includes r. So if you follow that method, it will give you exactly what's in the paper. And then if you multiply that again by the rotation matrix in the z-axis, then it will give you the TW transformation matrix that's in the paper. So
and, yeah. No, I was just
can we go to the simulation?
Yes. So the only thing is the way I did it is rotation. I just used the normal DH table, rotation Z times translation Z times rotation X times times translation X times rotation X, and I got to the same result of the TW table. So do we want to run the simulation?
Yes.
Okay, so I'll run it here. And it's running. And that's what we get in terms of the end effector trajectory in 3D and as a 2D plane of what we're seeing.
That is exactly what I get as well. So if we use the other method, you want to share my file or just?
Sure, I can. So now if we go to your file, and then I'm running your file now, and we see what we get. And we get the same trajectory over the same basically workspace, so it looks very similar. So that proves out the concept that we can prove the final result in the book in 2 ways, or in the paper.
Right.
Yep.
So if we go to the actual assignment here, let me share. So it means that we have been able to derive equations 1 through 3, which is the problem set 1 for this assignment. The questions that I had was, so we did the simulation based on problem set 3, setting out at 1.5 millimeter of radius, which is the same number that you were using on the MATLAB.
Yep.
And also, but then again, we're supposed to do that similar approach on reference 1. And I'm having a really hard time about reference 1, really. So if we go to reference 1, which will be this paper right here.
Okay.
So it basically, what it's saying is we have to be able to use a different length on each one of the cables to make the manipulator different shapes, which means that in our design we only have S
and R.
And correct, R is a constant.
R is a constant because it's constant arc length, but we are going to go in every S that is available, and we're going to change that S with what they want there, and we can, I think that's what we need to do, right? So we'll
right,
have,
but it talks about these equations right here, which I try to figure out, like back and forth, going up and down, what is what, and it, at some point I lose the relationship between one paper and the other.
okay.
So if we keep in the same paper, designed for kinematics, and we keep going down, there you will see S here.
Mm-hmm.
And then R will remain the same.
Correct.
And then we're supposed to find the S for the different
links.
Length, right?
Yes, for each link we'll have a different S. So you will have an S1, S2, S3, and S4, right?
Okay, that's so where would those S go? Would those be on the DH parameter?
The S will be on the DH parameter, yes, because the S is going, so everywhere you have a theta, 2 will be substitute. So right now you just put theta 2 as, I think, S over R divided by 2. And we put it general in all of them. Now theta 2 will be different from theta 4. So theta 1 will remain the same, but theta 2 and theta 4 will be different, and D3 will be different.
Right, so if we go to the DH table, here,
it will be KS1 over 2. And then here, it will be KS3 over 2 in the D3 parameter, 2 divided by K, sine KS3 over 2. And then 4, it will be KS4 over 2. But we need to find the value of S2, S3, and S4, and then plug them in there.
So why is it here S3? I mean, This is var theta. Why is this 0?
I'll tell you. So I was having a difficulty with that, and in the first paper we read, which is this one, it was referencing an aerial work, which I found very interesting to explain. The DH table looks a little bit different, but then they modified it here. Let me share that with you, and I think it will make things a little bit easier. I have to open that. So you're viewing my screen, right?
Not yet.
Okay, so let me, 1 minute, I will open it, because I was having a difficulty understanding visualizing it, and this really helped out a lot with the visualization. So it's Hanan Walker is the one there, and then I will zoom that, and it was referenced in that presentation.
In the document?
In the document, yes.
Okay.
And I downloaded the article. So here it is. So can you see my screen now?
Yep.
So let me scroll down to so this here representation is what they use to derive their DH table. And I found that very, very interesting, because it drives the point through. So he's presenting it, he's making that arc. So first off, he went there and said, it is something like this. This is your geometrical presentation. He's showing you the arc here, and he's showing you the line from here to here. And this is your start, this is your finish. Now we go to how he presented it in terms of the robotics. So he said, the first link is your base coordinate system, and that's Z0. So if you can visualize, you can rotate it 90 degrees to visualize it, but basically that's your Z0. And then your Z1 gets you to, is going in the paper, and then the Z2 gets X1 to go to X2. Exactly. And then D3 is the translation to the other side. And then basically Z3 moves it to X4, so it's tangent. And then Z4 is basically your endpoint. He did only 4 links. The 5th link that we have in the paper, I never understood why he's doing this in our paper, is he's putting it back in the plane, in the 2D plane again, and I don't know why he's doing this. But this one is not, and this one will look exactly like the one we have, except the 5th link, which is putting it back in the 2D plane, and the alphas are just opposite. So instead of 90, it's minus 90 and 90, and then, so it's the same order, but they are opposite to what you have here. But I found this, and I'm gonna use this as a reference to explain, because this really helped me visualize the snake robot in terms of rigid links. Does that make sense?
Totally. Yeah, this is really helpful because it also helps explain the other document as well. So things that you couldn't figure out there, you can see them here.
Yes.
So the asterisk under theta.
He's just saying that the variables are the SES. So he's saying for link 1, it's theta 1, theta 2, link 3, theta is 0, but you have it's a prismatic joint, and then the 4th link is rotary joint. So 3 rotary links and 1 prismatic. So basically he's presenting it as a wrist, prismatic wrist. No,
so if we were
wrist, prismatic, and then.
So if we were to do the 6th section robot, which is the continuum robot, he wants us to simulate.
So
So
should
it
I,
means,
do you want me
so
to
we
stop
have,
sharing and you share now?
can you send me this document, or is it
I
uploaded
already
in
put
this?
it, I already put it in the file.
Very good. So I'm gonna bring it up. 1 second.
I'll have you share now so you can share what you think. And then it establishes up there geometrically, it establishes very easily the relationship between thetas and is, but in the work we're doing, it is, they modified over, they're referencing this document and modified over it a little. But that's the basic concept.
Okay, so I'm bringing it up. 1 second. Download. There you go. Okay.
Yep.
So let me bring this one smaller.
And you want to bring them side by side to visualize it.
Yeah, that's a better idea. So if we take this as reference, do you see my screen?
I do.
Okay. So if we are to map 6 different sections, being the 6th, the N effector portion, this will be 4. So it means we need 2 more. And based on this design, I guess the next portion would be also another prismatic. So adding, if we look here over C4, and we want to add 5 and 6, then it will be like
Repeating
cropping,
it again. Yes.
cropping
So,
it here,
yep.
and
That's
then
what,
doing an.
yes. So you're
So let
just
me.
repeating it again.
Let me
And
do some.
I don't
Give
know
me
if
one
this is right,
second.
or I'm leading you off a wrong track here, but that's what I would do.
So I guess we can map it out and then do it in MATLAB, and if it doesn't make sense, then we were wrong. So I guess what I'm saying is this will be like that. C4. So this will be D5.
Correct.
D5. Then
Z5 is in the table. Is
D5. D3. So theta 6. Oh, I'm the worst.
No, I'm worse than you. And then Z6 is going inside the paper, right?
Right.
Z5 is
So
continuing on Z4, and Z6 is going
C5,
inside the paper.
C5, and then over here will be C6.
Inside the paper, though.
Who?
Yeah.
So this is C4. So here you got C2, and then going inside the paper was C3, D3. Then so C4, C5, D3, 4, D5, D6. I think this is okay.
I think it looks right. But still, it doesn't solve our problem of the relationship of the S's.
Right. Let me. This will be at least the first part.
Yes.
Oh, wrong class. Um, okay, so now that we have a similar coordinate frame, this means that there were variables. Okay, it's not telling us much. This is the n effector homogeneous transformation. Oh, it has L everywhere instead of S.
It is okay.
Okay.
Yeah.
But L without a number, so it's using it as they are all the same. This is Jacobian. It's going too far.
Yeah, we're not going through the Jacobian this time, at least.
But here is when it actually uses KI, LI. See?
Yes.
So essentially, that's what we need to do. We need to call it LI, KI. KI was supposed to be a constant. Does it vary if depending on the link as well?
No, the case shouldn't vary because it's using the concept, if I understand correctly, of a constant arc length. So as a constant arc radius, I'm sorry. So the
Right.
radius of the arc should be constant. So I
Right.
think
It doesn't vary because theta is the one varying.
yes.
Okay.
So I think for us to have our model, if you scroll up again, Alfredo, to T04, yeah, or A04, whatever they have it. So basically, once we get to our, so we are going to increase the links 5 and 6, and then we can do S1 through S6, which is basically your SIs, and then basically we do the normal transformation matrix, and then we got it. So the only thing remaining is to find what contributes to S1, what contributes to each arc length being shorter or longer.
The S itself, I believe. Let me go to MATLAB here real quick.
So if you want to open the one I have the DH table and just we can finish it from there, I can do that too. Ah, you have mine opened already. But this one is the normal, is the one with the DH table as in the book. It's not the one from Hanan. The one from Hanan, I have it too if you want it.
Yeah, why don't you share now? Okay.
So do you want, so I share the MATLAB one?
Yep.
So, okay. So, but I think, so here, different DH table. So the DH table here looks a little bit different. As I mentioned, it has, instead of minus 90 and 90, it has it the opposite.
The opposite to the previous document, you say?
It's this, it's the Hanan document, the one that I just showed you, is the
Yeah, link one is still positive, so it's good.
no, in yours, in the books one, either. Ah, so it's the same. I thought it was the opposite.
Yeah, they look the same in this case. So I guess we can just go into the DH table and create two new rows.
Correct. So what will the fifth row look like? It will have theta will be, because it will be a translation one, so theta will be 0.
Right.
And then the D, that will be your D, and then 0, and then
Minus 90.
will it be minus 90 or it will be 90?
Well, you're doing the fifth row, right?
Yes. It should be 90 like the third row.
Well, the third row is minus 90. Oh, see, there's something weird here. Wait, 90. Oh, I see what you mean. In the design kinematics, it is the opposite.
Yes.
So you were right. You were right.
Yes.
So yeah, go opposite to previous row, 0, 0, minus 90. So 1, 2, 3, 4. So it should be positive.
Positive 90. So should I
Yep.
do it the same way? I continue with that, or you want to change it all to like the previous paper?
Let's change it all to the design and kinematics document.
Okay.
And if we have something wrong, then we will change it.
So we're going to go here and do that as minus 90.
Right.
The second one will be 90.
And minus 90.
Minus 90. 90.
90. Minus 90.
But even that is different because you remember the fifth link in the design kinematics, it only had theta 1 and all zeros. It was returning you back outside of the plane.
Yep. So that's theta 5, opposite to theta 1.
Yes, or minus theta 1 basically, yes.
So this means that now the end effector will be equal to theta, and theta 5 will be the displacement with 0 being theta 5, 0.
I don't know, is that what we want to do? Or, I mean, we're thinking.
Yeah, if we follow the VH convention, the normal way, that will be 0. So let's do it how we are used to do it.
So doing it, so the last one will be what? Will be, so we'll keep number 5 as it is, and the last one we'll do it as theta 6 and all zeros.
Yep.
Okay. So basically what we did is we just added a displacement one, right?
Right. So 1, 2, 3, 4, 5.
And this will, that and one will be in the same, it will not have a, will it have an alpha of 90, of 90, right?
The N1, well, in the document here, it doesn't have a 90 alpha. It is stated as 0.
So
Let
we'll
me
do
see
it this
here.
way. Yeah, we'll do it this way. Here we will say theta 6. Now, are we going to make theta 6 equal to minus theta 1? Is that what we want?
Let me see. Theta 6 equal to, is it theta 4? Because based on the document that you have, the Hannah Walker one, they make, let me share real quick. So if you can see here, they made theta 4 the same as theta 2, which is this rotation right here equal to this rotation right here. Because it cannot be equal to C2 because this is a prismatic or seen as a prismatic. So which means that if we go to our drawing here real quick, that theta 6 then will be the same as theta, well,
Which
as
is the,
theta 4,
which is the same as theta 2.
which will be the same as theta 2, correct.
But we are okay. So let me go back, but we are going to do different S's here. So
Let me stop. Okay, yeah.
I'm just sharing again.
Yeah, share again.
Do you see my screen now?
No yet. There you go.
So here what we're going to do is we are going to call it KS/2. So this will be, so we start from the beginning. So we have KS1, and then this here will be the S2 S2, and then theta and this is not going to be theta 2 anymore. It's going to be theta 3. I hope you're following what I'm doing.
Not yet.
Okay. And then so I'll just call this. One second.
Yep, you're adding the numbers now. I got it. So we only need the end effector link, right?
Yes. So I made here theta 2 is KS1 and D3 is S3 divided and then here
Why are you using S3 over theta 2 for D3?
so D3 because there is no theta 2, so what will D3 be equal to?
Well, based on the DH here, D3 is 2 over K times sine ks over 2.
Exactly. Okay. So okay. So we'll just put it this way. Yeah, I don't know why I did it this way. You're right. Good catch.
Ks over 2. Over 2.
Like this?
Yeah, and you should multiply, well, 2 over k times sine of ks3. So the first 2, yep, that one. So it's 2 over k times sine, correct.
Like that?
Ks, yeah, ks3 dash, yep, that is correct.
So that is D3. So we can just go here to theta 1. Yes. We'll just go and put D3 here. What do you think?
Yeah,
You agree? Yeah.
yep.
So we put D3 here. Then we have S4. And then,
Well, theta 4, why are we using, I know in the model it's supposed to be equal to theta 2 under specific circumstances, but we want to know when we change S4, what will be the impact on the robot. So we have to maintain all of the S's live, so it works. Do you agree, or?
I totally agree with you. Yeah, it's getting late, and that's why both of us are checking each other out. I mean, confirming, yes. So, and then what did we say we're going to do with theta 6?
So theta 6 should be a prismatic. No, wait. Let me open this again. So theta 5 is prismatic.
Yeah, there is no theta 5. It's prismatic joint.
Where is it? So you should have D5 somewhere.
Yeah, I'm going to get to it right now.
Okay. So 0.
So you've got theta 1, 0, 0, minus 90. Theta 2, 0, 0, 90.
Can you run it?
Well, I just want to go through the variables, make sure we have it right. D3, 0.
Yeah, it's just the other way. I see it better.
When we run it, you see it better?
Yeah, if it is the same as the DH table below, it will be easier for me.
Okay, I will run it. The only thing I don't have is, so what do we need now? We need S2.
You need all the S's as for no S, no S1, no.
There's no S1. Because theta 1, you remember, is getting it in plane. You agree?
Yep.
So let's run here and see what we get if it runs. Yep, theta 6. Okay. We need to know what theta 6 is, but we will. Theta.
Oh, the comma after the 90. Yep. Let me call them. There you go. Okay.
That doesn't look wrong. I mean, I don't know.
Data.
So we've got the prismatic, the revolute to get it in plane, then the first revolute joint in the plane, then the prismatic joint, then the revolute joint, then the prismatic, then basically theta 6 for the end effector.
Yep.
Now we need to know what theta 6 is.
And so on your document, the last, so alpha.
So theta 6 will be a function of S6, right?
Yeah, and alpha 6 should be 90.
That's what I originally thought. So we had it 0, so do we need to put it to 90?
That's what I think.
And then do we need to go here and say theta 6 is equal to K?
Yeah, the same thing with theta 1, I believe, because there's still a cable for theta 1 for section 1.
So will it be K times R? But I don't know what we have. We don't have a value for K1, for section 1. So we'll do it the same way. So theta 6 will be, so if that's the case, then theta 6, if it's out of the plane, it should be minus 90.
Should be a what?
Minus 90 for alpha. because in the design kinematics, they return the last link back to make it like the very first link, get it back out of plane, you understand?
Yes. So I guess you usually would do, so you went up or going out of the,
You went in and went out again, so you want to put, that's why you want to put it 90?
So yeah, I would do opposite to what it was, because we were going right, then going up, then right again.
Okay. Okay, I think we're, so let me run it one more time, but I think we're still missing something. So that's theta 1. So we need to explain theta 1 in terms of the first segment.
That is what I think too. Yep.
So basically, when he says pull and push, all what you're doing is just you're reducing the value of S or increasing it.
Right.
That's all what you're going to be doing in the program.
That is correct. So if we, for example, if we pull the value of S2, S3, and S4, we should have a robot, and if we are in the 0 plane, we should have a robot going up session 1, then it makes a curve, session 2, 3, and then session 4, and then session 5 and 6 should go straight. So you will have kind of a, like up, left, round, and up again. So if that happens, we got it right. Great.
Okay, so now let me continue the piece here. So this one is, and just to continue the table. Okay, so we've got A5 as DH, G05, 6, 6. I just want to make sure I have it right here. So. Yep, that thing that doesn't look. Do we want to simplify them or just keep moving for now? To think we need to just see what we're getting, right?
Yeah. So
we'll have to do a value for S1. So the K's are all the same. We just have to do S1s to S6.
Yep.
So I will try to run it with all the S's the same for now, just to see if it runs. You're okay with that?
Yes, sir.
See what we get. Because we should get the same plot that we originally had. No, it will be a little bit different, won't it?
Looks pretty.
Doesn't mean it's right.
Okay. So are those all of our variables? Is it the S's, K is constant, we have it constant there. Theta 1. So we gotta.
But it's
So we gotta say what the other thetas are, right? Or theta 1 is the only.
No, we even said theta 1. We represented it, if you remember, as a function of S1.
Okay. Then we don't need to state any of the thetas, right?
No.
Only the S's. Okay. Okay, go down, go to the variables again. Keep going. Okay. So comment out theta 1. No, I mean theta 1.
Theta 1.
Two.
Theta 1. I
That
just
one.
it out, but it's not being used anywhere, so.
Okay, just in case. Lane space. So we are using the same. Oh, from 0 to something. Okay, so let's play with this. Let's make the first value on the S's. Let's make the first value the same as the second one. And then let's pick 3, 4, 5 remain the same. You get what I mean?
So S1, the value
S1.
of, yes.
So let's delete that number for now. Let's put 10 and 10. 10 and 10.
So
the
what
first value is,
you wanted in millimeters, Alfredo, so it has to be 0.01.
Well, if you could put in the figure, you state that whatever you're seeing is in millimeters, and you're good. But anyways, you can do that too. You know, it says 0.01. Make the first one to be 0.01 as well, so that it doesn't sweep.
So on the K as well?
I think I can take control. Let me see. Request remote control.
Okay.
Technology.
You want it. So okay, I see what you're doing here. So you're basically, why don't you do, you're going to zero them off and just move one link at a time and see what it does.
That is correct, sir.
Yeah, I understood where I first didn't get what you want to do, so.
That you can get control now.
Okay. So we're going to do S3 and 4 and 5 like S6. Right?
No, those three, we want to have a value so that we do kind of a, let me draw it. What I want to do is, so 1, 2, 3, 4, 5, 6. So I'm drawing something so that you can see. It doesn't look too good. No. Okay, I'm gonna draw it in paper so that you see it. Let me get,
So
let me share something.
Yeah, I'll stop sharing, so you go
Okay.
ahead.
You are controlling. Give up remote control. Okay, there you go. So I'm gonna share this once more. You see my screen?
Yes.
So what I'm saying I want to do is, okay, this is 1, and then 2, and then 3, and then 4, and then 5, and 6. I don't know if this is possible, but this is what I want to do. So let's say this is 10. This is always 10, so this is constant. And then this goes from 10 to 20. This one goes from 10 to 20. This one goes from 20 to 10, I don't know, something like that. And then this is back to 10, constant, 10, constant. Does it make sense?
10 to, okay. So you are, where you're making the loop, you are basically starting at 10 and then you're making it bigger to loop
Right.
around. Okay. 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 So you're keeping 1, 4, 5, and 6 constant, and you're varying 2 and 3.
Well, actually, I'm keeping, I don't know, we could do it that way and try it, but here, 1 is constant, 2, 3, and 4 are varying, and then
Okay.
5 and 6 constant.
I got what you want to do, yes. And then we'll see if we can imagine it, if it's going to give us this or not. Now I get you. So we're going to keep 1 constant, 2. We are going to vary, so 0.01 to 0.02, for example, and 3, 0.01. 4. Yeah, we can experiment with it and see what we get. And then we said we are going 5 will be 0.01 and 0.01.
And then instead of using 181, we should do 0.00. No, that will be,
No, these are the number of times.
yeah, number of times. So 1, 2, 3. We should stop it at 100.
So it doesn't loop. Basically, you wanted the same number.
And
Okay.
don't forget K.
So what do you want to put at K?
It's gotta be the same amount of samples, so it's gotta be 100. No, that was good. That was okay.
Yeah, because I thought that's okay. Yes, you are right. Yeah.
All right. Let's see. Here goes nothing.
Yep. But I think at least we're close. We have a model.
Right.
Still running through.
Maybe if you rotate that chart, maybe it has it. Click on the chart.
Here?
Yep, that one. And then on the rotate icon, now you can like move her around while you have the rotate icon in your mouse.
I just have the zoom windows are appearing. We're trying to move them. I don't, yes, here we go. Okay, so like this.
Well, you can go to a figure. Yeah, that might help.
No, it's not doing anything. So now I made it bigger.
You should be able to hit the rotate icon, and then you can move the direction.
I'm hitting it, but
I am not seeing what you're doing.
oh, you're not?
No.
How come? Did I stop sharing?
No, maybe you're just sharing the application and not your screen.
Okay.
The one thing I need is a good camera. I need to buy one.
I can't find my Zoom icon. So I used to, I just, where did it go?
Should be in the right corner somewhere.
It was there, but then I clicked on something and I'm primitive in some things. I try, but sometimes it's just.
Yeah, everyone is.
So I see yours, but I can't see mine. What do I do? How do I get that back?
You mean, do you see a small screen?
But it says join meeting. Should I join meeting again? But I'm already in there.
No. That's not the one.
I see your screen.
You see my screen? I'm not sharing.
No, not your screen. I see your icon. I mean, your face.
Okay. So yeah, click on it.
Okay.
And then right click and do something.
So when I right click, it does say chat and pin video. Why don't I? Should I give you? The problem is I can't do anything.
Let me see if I can. I'm gonna share my screen and see if it helps you out.
Okay.
Did it do anything?
No, I see your screen very small. So why don't I just?
Oh, I think I did the same thing now. So you gotta double click it maybe.
You see, I hear you and everything, but I can't see where the Zoom icon went.
Oh, so you gotta hit the equal sign so that you see both of us. When you go over that little screen, hit the equal sign, you should see both of us.
It's doing nothing.
No?
I think what I need to do, maybe if you drop the call and then I join the meeting again.
I think, oh, okay. So you have two screens? Do you have two screens in your computer? Are you using two screens?
No, just one.
Just one. If you put your mouse up top
Yeah.
in the center, if you move your mouse to up top in the center, can you hit stop sharing?
So but I'm not sharing. The only thing it gave me here, do you want to leave this meeting? So
Yeah, leave the meeting and come back.
I'll do that.
There you go.
Okay. So I'm going to share my screen. Then here it is. So
Okay.
I don't know, it looks like it has a little bit of a bow to it.
Yeah, very small one.
So maybe we need to just play with the variables a little bit.
Yeah.
Okay.
Well, can you do a lot of zoom out? Like, do a lot of zoom out?
A lot of zoom out, okay.
Yep, that's. No, you gotta, now that you have that, the loop, you gotta touch over the graph so that it zooms out. Or you could do control, scroll out, and it will do the same.
Well, I don't have a mouse with me. I just have the.
Let me take control. Let me see if I can.
Okay, see if you can make it work. Bless
Sorry
you.
about that.
No, you're fine. Bless you. Yeah. So why don't we just go there? Yeah. If you want to.
Yeah, it won't allow me.
Yeah. So, yeah, I did the same thing. Why don't I go in there and just change the parameters?
Yep.
So we want to go from 0.01 to 0.03, for example, or do we want to go from a smaller value?
Um.
Or 0.01 to 0.04? I
Oh,
think.
wait. Yeah, if we have a small curve, is it curvature?
Yes.
With K, you will never see it if we're talking thousands versus hundreds, K versus S's. So make K bigger or make the S's smaller.
So make K bigger. So we add another 0 to the K.
We remove another zeros.
You remove another
Oh,
0.
you add no. Yeah. It is dividing it. So
I don't know if you want to make it bigger or smaller though. Because let's look at what we have here. K. So if you make K bigger,
so 1 over 0015 is 666.
yeah.
So our S values should be bigger.
I think so. Should we make it 0.1?
Yeah, let's try that. So next time you could do a session break over K. So you just hit run section and it goes faster.
Okay. Yeah, I see what you're saying. Yep. Sort of did something here.
Yep. Read on everything. Yeah, that title, make it smaller so it doesn't take the entire graph.
Which one? The
Both. Just remove a lot of things out of the title. Yeah, that's okay.
okay, so you want to put a section break
Over K, above K.
right here?
Yep.
After T06, right?
You could do that as well. Yep.
So here,
Section break.
and
Now
then we
you
just run.
You just click in the section you want to run, and that will do the same thing. You gotta say run section, so it doesn't calculate the whole thing again.
So where do I find run section?
On the upper right to section break.
Run section, yes.
That's the one.
That's a cool trick. So now it's running, or should I? Yeah, it's running. It looks like it's doing it. Or should I hit run again?
It did run already.
It did run already, yes.
What did we change? Nothing?
No, we didn't change anything.
Okay. So maybe we just go like all of them the same, and we can make one of them like 0.3. So we start one by one and see what the effects are.
That's what I was thinking, yes.
Well, do one in the middle, not that one. Keep that as one. Yep. And then one, or do that, make that the one in the center. You can make that like 5.
The S3.
Yeah.
And then we'll keep everything else at 1.
Well, actually, S3 was a prismatic, right?
S3 was the Prismatica, so there's no point of doing it.
Right. You gotta do 4. Yeah. Let's see what we get there.
And we're not moving. The prismatics need to move, because they will affect the shape a little bit. Oh, did I run the whole thing?
Yes. Yes.
Yeah, sorry.
Yeah. I don't know if sometimes when you evaluate, I think the value is kept. So, oh, there you go. Rotate that one to see it.
You can see it, right? You can see my screen?
Yep.
Yeah. So it's doing something, definitely.
Yeah, so at the end, you see that at the end, it went like crazy, right?
It went like a hook. Yeah.
But it was like smoother at the beginning,
Yes.
and then it did like a curve.
Which is follow
So,
the leader. Follow the leader concept.
right, so that is because of the 0.5. So
Correct.
the 0.5 angle is breaking it further.
Exactly.
So it is working.
It looks like it.
Well, it is, here it is 1 a.m.
You're
So,
tired. You're done. You're done.
So to me, it can look many things.
But I think we got it at the end.
Yeah, I think it is a good practice what you do on the other drawings. Maybe we also need to add like a top view,
Okay.
and because on a top view we would see that curvature that.
Well, I do have a top view, yes, and it is. I already have a top view. Let me share because I was just going to tell you it's 1 o'clock. So the top view is just showing
No,
it's
got to be a right view then, or left view.
how do I just put left view?
No, you gotta plot.
I see what you're saying. Y versus
Y and
Z.
Z.
Y and
Right.
Z. Yes, 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 yes. Sorry, I'm going nuts here. But it's good. I think the base program is not so bad. Huh?
I think we got it.
Okay. And you have work tomorrow, I have work tomorrow, but you are, as you said, it's 1 o'clock your time, so I think you need to
Yes.
sleep. Are we going? I don't feel we have time for overleaf. Do you want to do overleaf, or what do you want to do?
Yeah, we need the extra points. So we gotta do. I can handle overleaf.
Here you go.
There you go.
Yeah.
Let me get this out of the way. So it has normal curvature, but all of a sudden it goes left.
Yeah.
Maybe make that value a little bit bigger. Instead of 0.5, use 1. Let's see what we get.
You just want to verify, yeah?
Yeah. No. That's the whole thing.
I ran the whole thing.
Yeah,
but
you gotta hit run section.
Yeah, I know. It's fine. Shouldn't, yeah. Here you go. Yes.
But
I think the model, I don't know if it's 100% or not, but let me, because where are our prismatic ones? They are S3 and S5, right?
right.
So I just want to, well, no, let me do just S3 for now. See what it does. So I kept everything the same, and I just changed one of the prismatics, and
Yeah.
it should show that.
Yeah, the problem is we are sweeping them. So these are all, the sizes should be, okay, let me see how, in order for us to see what I was saying, we need to use constant, not values from X to Y. You see what I mean?
Yes, you want to keep the prismatic constant.
The number constants to see that, well, it is working, but
Yeah, I think
yeah.
I just wanted to verify that when I do the prismatic, it changes it into an oval shape, and it does that.
Right. It works.
Yeah. That's so basically your prismatic is just giving you a longer reach.
That is correct.
So I think we need to break for now. I think so. Here is what I'm thinking for the paper. We need to have the section, and I mean, I don't know how you like to do it. We can do it in problems, but I like to do it as a homogeneous project. So we can do section 1 of it. Basically, when we're going to have abstract, introduction, methods, just as he wants it. Results, discussion results. So the methods, we're going to say the first method is we just implemented what was in the discussion paper, and we implemented that in MATLAB, which is your original program. And that's what we got. Method number 2 is we wanted to verify that if we use that same DH table, we can get the same result. Yes.
Right.
So, and that's the program that I put, and we put that in there. And then the third thing is we'll probably have to draw the schematic that was in the Hanan paper, but add to it that extra section and say we use that paper as a building block, and we just repeated the prismatic again. And this way we have our 6 sections, and then we can say if we pull or we push, that's what we get.
Phenomenal. That's exactly it.
So I mean, how do we want to, I'm just thinking, how do we want to, we can do it in one of multiple ways. I can put the program, which is, so basically there are 2 programs that I will make sure they are loaded in our file share. The one that we were just working on for the past hour, and then the original one, which is equation 1 and 4 and the factor plot, which is already there. So I can load that extra one in there. And then do you want me to write, I mean, if you're more comfortable with overleaf, what I can do is I can do abstract, introduction, methods, and I can even put some points on conclusions, and then you can continue and edit. And I don't know if you want to combine all 3 programs together or how you want to give him the MLX file.
So yeah, I would, so we need to, in the results section, we need to add the code for the both of the papers, like the 2 or 3 methods that we did. So the code has to be there.
Yes.
So I would do that. I can do the discussion.
We'll need to add the graphs as well. All the graphs, we'll need to add them in the results or in figures.
Correct. We need to add all the graphs in the results. And then in the discussion, we need to talk about the methods that we use and the results that we got, like specifics to the formulas. And as you were saying, like describing what we got out of the assignment. And then in the conclusion, we just say, so we comply with the objectives, we learned this and that, and we were able to make a continuum robot work, etc.
So what I can do, Alfredo, because I still know you have the other assignment and I really want to help you out. I mean, we as a team want to work together, so I can finish up the abstract, the introduction, the methods, and I know the results will take a lot of work. I can put what I can in the discussion and conclusion. And then you add the results and the references and see if you want to add anything else. Is that fair, or you want me to do something else to help you?
No, I can certainly, if you can, is there like a specific format you want to follow, or are you good if I just go and pick up my last project and use that one? Because on the one that I have, it already has a format for the references. It has the format for the M code or MATLAB code. So you want me to start the project in which we're gonna be adding the information?
Yeah, if you want to. I thought that we are going to do the format of abstract, introduction, methods, results,
right. It's that same
conclusion.
format.
Yes.
Yep. That same format, but it already has the code for bringing up the MATLAB code, the references is easier.
I think that would be great. Yeah, and so if you start it, I can write the abstract, introduction, method, and discussion and conclusions right there in the overleaf.
All right. So I'm gonna start that now, and then
you're gonna share it to my email, right?
I'm gonna put it in the discussion.
So I thought that you are going to do it like Catherine did, so that we can. How are you going to make it like a live folder so we can both access it at the same time?
Yeah, I need to invite you. So let me enter right now. Give me 1 second.
Okay. But looks like we make a good team, huh?
We do, man. Thank you so much.
No, thank you.
Saved my life today. Let me get this. So should I still stop recording?
Yeah.
Okay, where is it?